some vocab that you need to know. Constraints. Constraints are kind of another way of saying the restrictions on the graph. And so for us, our restrictions are going to be the inequalities. And then we want to talk about the region, just like what you just did on the homework quiz. The region that these inequalities make when you shade, we call that the feasible region. And so those are words you're going to see, just some vocabulary as we go forward here. So when we talk about these regions, we have two types of regions. One of them is what we just did on the homework quiz. When you graph 3 or more lines and it makes a closed shape, we say that if your shape is closed, that is called a bounded region. And if you read that little paragraph there, it says, if you have a bounded region, the maximum and minimum value will always occur at one of those vertices. So the reason that we did that yesterday is because today you're going to be able to do this, and then if you take these 3 vertices and you plug them into this equation, you can figure out what is the maximum or the minimum of that equation. The other type of region that we might have is we could have 3 equations that don't make a closed figure. We did not do that yesterday. If one part of it is open, we say that is unbounded, because unbounded means it just goes on without restriction. Unbounded regions will either have a maximum or a minimum, but they won't have both, all right? So depending on what the graph looks like determines whether it's going to have a max or a min. So think about this one for a minute. Looking at this, do you think this one's going to have a maximum value and no minimum? Or you think it's going to have a minimum value and no maximum? What do you think? I'm just going to sit here and wait. Why do you think it has a maximum but not a minimum? So it has a top line, which means it's probably going to have a highest value. But if this keeps going forever and we keep shading all down here, won't this just keep getting smaller and smaller and smaller? So I agree with you. Like, you're right. Like, it has a top value. There's a top point. But think about, like, this goes down shading forever. So, like, -100, -1,000,000, right? There's not going to be a minimum value. So you just have to kind of look at it, and we'll do one, hopefully, like this in a minute, that you'll see that, like, this one would have a maximum and not a minimum. If it was shaded the other way, like, if it was shaded like this, like starting at this line and shading up, it would have a minimum value because it has, like, a bottom portion, but the top goes on forever, and so it wouldn't have a maximum value. So that's what I mean by it'll just have one or the other as we do this. Okay? So let's look at some that are just math, like there are no applications, and then we'll do a story problem to end. Okay? So if you just read the first 2 sentences here, it's exactly what you just did on your homework quiz. Graph the following system of inequalities. Name the coordinates of the vertices of the feasible region. They give you 3 equations. You could graph it and make the shape. The only new part is, then it says, find the maximum and minimum values of the function, and they give you this weird function for the region. All right, so that's the new part. So step 1 is let's just graph just like we did. And again, these vertical and horizontal lines are going to show up a lot, so you'll want to make sure you feel comfortable graphing them. So when x is less than or equal to 5, I'm going to go to 5 on my x-axis. And again, I don't usually shade on these because I just look for the region, but if I get confused, then I'll go back and shade. But less than 5 would be going like backwards. Y is less than or equal to 4, so I could go up here to where y is 4, and that is a horizontal line everywhere that y is 4. And less than that would be like below here. And then if it's not in slope-intercept form, just like we've been doing all year, you got to get y by itself. So to do that, I'm just going to subtract x over. So I would have +2, down 1, over 1. And since I want to know where they cross, I always, even though it's graph paper, sometimes my lines aren't very straight, so I just make a whole lot of points until I get to where it runs into the other line. I don't know if you do that or not, but sometimes my lines aren't very straight, so I just make a lot of points sometimes. And again, this could have been on your homework quiz today, where you see that triangle. This would be our region that we've made. And just like you did on your homework quiz, we want to talk about these points where they cross, which you want to make sure you write them correctly, unlike what I did on the homework. So what would that be? That would be the point -2, 4. Do you agree with that? And this would be the point 1, 2, 3, 4, 5, 4. And then this one down here is the point 5, -3. So the new part now is they've given us this function. So first of all, this is a function different than how we normally write a function, because normally we just write f of x, and we just have x over here. So notice that they have two variables here. It's just because we have two variables here, and so don't freak out too much about that. But we're just going to take each of these points, we're going to plug it into our equation, and the biggest number that we get is going to be the maximum, and the smallest number that we get is going to be the minimum. So I'm just going to take this function, and I'm going to say f of my point, which is -2, 4. So instead of just f of x, I have f of xy. And I'm just going to plug that in. So you tell me if you're okay showing not a lot of work here. 3 times -2, I'm going to say is -6. And -2 times 4 would be -8. So that would give me a value of -14. And I'm just going to do that with all 3 points. So now I'm going to plug in f of the point 5, 4. And when I plug 5 in for x, 3 times 5 is 15. And then -2 times 4 would be -8. Check my math. I think I get 7. And then I'm also going to check 5, -3. And when I plug 5 in there, I get 15. But now -2 times -3 gives me a +6. So that one gives me an answer of 21. I'm trying to find the max and the min. First of all, that's a bounded region, so I'm going to get both. The biggest number is my max, my smallest number is my min. And it's just these numbers here. So like looking at this, we could say that the maximum is 21 because that's the biggest number. And the minimum is -14 because that's the smallest number. And you could really say the maximum is 21 and it occurs at the point 5, -3. The minimum is -14 and it occurs at the point -2, 4. You don't have to say that, but that's just kind of what you could say. So maybe this doesn't feel so bad, but it's like, what's the point of this? When we get to the story problems, that's where the point of it comes to play, because given a certain situation with given restrictions, like a business model, if you're trying to find out what should I do to make the most money, you could use linear programming. Or if you're trying to have the minimum cost, what's the least amount of money I could spend and still make this product, you could use linear programming. And so that's kind of the point of this. Okay, so let's do the next one really quick, and then we'll do the story problem. This is where that slope-intercept form is so important, because look at number 2. None of those are in slope-intercept form. None of them are just the vertical and horizontal lines. So the first thing you have to do is be good at algebra and be able to solve all those for y. Goodness, that sounded like a really long bell. So I'm just going to solve each of these for y. You do the same thing, and then we'll see if we agree or not at the end. As you get your equations in slope-intercept form, just kind of look up, and I circled my 3, and make sure you agree before we start graphing, because if we disagree, then we want to make sure that we all have the same equations. before we graph it here. That middle one I had to flip my sign because I divided by -2. So I'm just going to graph mine, hopefully as you're graphing yours as well. The first one? Only if you divide or multiply by negative. So on this one, I added x over, and then I divided by +2. So I don't flip my sign unless I divide by a negative number. Okay? Other questions on this? So first of all, as I look at this, it's not a closed shape. So you're not going to be able to know where to shade by just looking at the closed shape. So you have to actually think about where the shading overlaps, which again goes back to what we reviewed yesterday from Algebra 1. So you got to make sure that we can kind of look at this. So give me a minute to see what I'm doing here. So this one was less than. This one was greater than. So I'm like in between these two lines. But then this one was also greater than. So I think if I did this correctly, I think that's where I'd be shading. And again, that kind of builds off back what we did yesterday. So this is an unbounded region, which means we are not going to have both a max and a min. We're still going to check our vertices. And if you're not sure whether it's going to be a max or a min, hopefully we can kind of look at the answers to see here. So because we only have 2 points of intersection here, we're only going to be checking those 2 points. So I believe it's -2, 0, and 0, -2. Is that what you got yours to be? -2, 0, and 0, -2. Notice I haven't even looked back at this function yet. Do not ever try to graph this function because that's not what it's for. That's just what we're trying to maximize or minimize here. So now given these 2 points, I'm going to plug them into this equation and see what I get. And so I'm going to come down here. So, and I just like to write it the way that they do it. It's kind of a different function notation. So I'm just going to plug in -2, 0, and I would get -4. And then if I flip it around and I do 0, -2, I would get -6. Do you think that I'm going to get a minimum out of this or a maximum out of this? It's unbounded, so I can't get both. I only can get one or the other. Because when it's unbounded, you're only going to either get a smallest point or a biggest point. What do you think? Because what? So there's 2 ways to look at this. One way is looking at the graph the way Bailey is, and that's what I usually do. This is going on forever, so think about, like, this is just going to keep going up. X is going to keep getting bigger. Y is going to keep getting bigger. So there's going to be a point out here where X is like 50 and Y is like 32 or something, and I'm just going to keep getting bigger and bigger values as I plug those points in. But as I go back, I'm stopping here, right? Like there's like a lower bound here, which means there's a minimum value. Another way to help you if you struggle with that is if you get a negative number, not always, but more than likely, a negative number is going to be a minimum, and a positive number is going to be a maximum, if that's another way to look at it. So if I know I want the minimum here, that means I want the smallest value, which means that the minimum occurs at 0, -2, and it is -6. This point's just nothing. It's not a maximum, but it's not a minimum either because it's not the smallest value. Questions about that? Yes.
So we have to apply infinity to the maximum or just
No, because there is no maximum, so you can't give a value because it just keeps getting bigger. So if it's unbounded, you only give one or the other. Okay, so now let's look at the story problem, and the story problems are a bit overwhelming because there's just so much information, but we're going to do one together, so hopefully help you do the one that I gave you on your homework. So first of all, the word here that we're talking about when we do these problems is optimize. In calculus, we do optimization problems a little bit differently than this, but to optimize something means to find the best price, to minimize costs, or maximize profits. And so this is where linear programming can be useful. This looks a bit overwhelming because it says there's 7 steps. Story problems. With any story problem, you're going to have to define your variable. What makes optimization problems a little bit more complicated is you have to define your inequalities for your constraints, and you have to write the equation that's trying to be maximized or minimized. So these problems are going to have a lot of words in them, and I promise the more you practice them, the easier they get. But starting with, this is what we've been doing. We graph the system of inequalities, we find where they intersect, we plug the points in, right? That's what we've been doing. The only new part is you have to write your system of inequalities, and you have to write the function that has to be maximized or minimized. Other than that, it's the same as the last 2 problems. So look at this problem, and let's kind of just read through it once, just to digest all the stuff that's going on in here. So a landscaping company has crews who rake leaves and mulch. The company schedules 2 hours for mulching jobs and 4 hours for raking jobs. Each crew is scheduled for no more than 2 raking jobs per day. Each crew's schedule is set up for a maximum of 8 hours per day. And on average, the charge for raking a lawn is $50 and the charge for mulching is $30. Our job is to find the amount of rakings and mulchings that would maximize the income for a crew. That's a lot, right? That's a lot of information. So step 1 is we want to figure out what are we trying to find. We should be having 2 variables because we're trying to maximize that function xy. So what are the 2 things? And it's like the very last sentence should tell you what your 2 things you're trying to find. Find the amount of rakings and mulchings that would maximize the income. So what are the 2 things I'm trying to find? Cody, what do you think? The amount of what? Rakings and mulchings, right? So those are my 2 things. I like to call them letters that go with it. So like I would use R for the number of rakings and M for the number of mulchings, but we're going to have to graph this. So if you don't like changing letters, you can call them X and Y, all right? So it's whatever makes the most sense to you. I'm going to use R and M and show you that we can just it's okay to use different letters. You just got to keep it straight. Mulchings. Is mulching really a word? Rakings and mulchings. That seems like a made-up word. The other thing that I like to do, like if I define my variable, I like to write that equation that I'm trying to maximize or minimize first because it helps me know what I'm not going to use to write an inequality with. So we're trying to maximize the income. So my equation that I'm trying to maximize should have the money part in it. All right, so up here I'm just going to write F of, and I'm going to do alphabetical order. So I'm actually going to do M first and then R because I think it should always be alphabetical order. How much money do I make for mulchings? $30 per mulching. So could I say 30M? Plus, how much money do I make per raking? 50. So 50R. And if you think about the equations that we've been maximizing and minimizing, they kind of had something X plus something Y, kind of representing whatever amount that we're talking about there. So that's what I'm going to use at the end. Oh, well, that's like, what have we done so far? We've defined our variables, and we wrote our equation to maximize or minimize. But what we have to do next is we have to figure out what inequalities are we setting up. And so that's all the other stuff that we haven't talked about yet. So here's a hint for you. Looking at my graph here, notice I didn't give you a full graph because in story problems, can we have a negative number of rakings and mulchings? Right? The minimum is 0, and so that's a constraint that you have to always think about with story problems. So my first inequality that I'm going to say, my first two inequalities, is I'm going to say the number of rakings has to be greater than or equal to 0, and the number of mulchings have to be greater than or equal to 0. So that doesn't really say that in the problem, but that's like real life. You have to think about it. Most of your story problems, you're not going to have negative. So now here's where the other part comes in. I think this sentence is the next easiest one to do. It says, each crew is scheduled for no more than 2 raking jobs per day. How could I write an inequality to say I cannot have any more than 2 rakings per day? So we know R has to be greater than or equal to 0. What does it have to be less than or equal to? Because I can't have any more than 2, right? So I could say R has to be less than or equal to 2. Carl, what are you going to say? So any kind of restrictions there. So then the other part, Carl said, what are we going to do with this 8-hour thing? So we know that you can't have any more than 8 hours per day. So that's going to go with the hours up here. It takes 2 hours for mulching jobs and 4 hours for raking jobs, and we can't be there more than 8 hours per day. So that's another inequality. It's going to be on this part for you. It's going to be less than or equal to 8. What's going to be on the other side? How many hours does it take for mulching jobs? 2 hours. And how many hours does it take for raking jobs? So could I write an equation saying the number of raking jobs times the number of hours it takes? Like 2 hours for mulching jobs plus 4 hours for raking jobs. So my total number of hours has to be less than or equal to 8 hours. And I think we've taken care of all the numbers that they gave me up there in that problem.
How many of these do we have on our homework?
But this is the application. Like, if we don't do a story problem, it doesn't make any sense what we're doing. Like, why am I making shapes, and what does the maximum mean? What does that mean, right? That's where story problems show you what you can do math for. So if we're graphing this, and I didn't use X and Y, you have to make sure you label your axis appropriately. So, like, again, alphabetical order. So M is the X, so I'm going to put an M right here, and I'm going to put an R up here just to help me keep that straight. Last hour, I did this exact same thing, only I wrote 4M plus 2R, and no one stopped me. Like I said, 4 hours for mulching jobs and 2 hours for raking jobs, which led to the wrong answer. And that's what Chandler was talking to me about when your class started. And that's why I messed up, because I interchanged the numbers. So if I'm going to graph these, R is greater than or equal to 0, M is greater than or equal to 0. It's up to you if you graph that or not. Like, those are, again, just your X and your Y axis. And so, like, that would just be this line and this line, because I can't have a negative value. R is less than or equal to 2. R is like my Y value. So R is 2 is right here. And that would be just this line right here. And then look at this one. I have to put this in slope-intercept form. So this is where you might decide, all right, I'm just going with X's and Y's because this is too crazy. But if R is my Y, slope-intercept form would just be getting R by itself. So that means I could subtract 2M over, and I could divide by 4, and I would get R is less than or equal to negative 1/2 M plus 2. And again, if you like X's and Y's better, on the one on your homework tonight, do X's and Y's. So if I graph that, I have a y-intercept of 2 and a slope of down 1 over 2, down 1 over 2. You with me on that? So if we think about this, like it's everything in between these two parallel lines, but it's everything less than this slanted line. So this is my shape here. So my ordered pairs are 0, 0, 0, 2, and 4, 0. Again, you don't have to show all this work when you're doing your maximum here if you don't want to. If we're trying to maximize the income, right, like this would be our minimum. We could make no money if we had no raking jobs and no mulching jobs, but that's not really helpful, right? Like if I plugged 0 into this problem, I'm just going to get 0 as my answer. So that's definitely not the maximum value. But the maximum's either going to occur at one of these intercepts here. So again, really important to pay attention which one's which, M and R. So this would be 0 mulchings, 2 rakings. So that would be $100. Is that true? 0 plus 50 times 2 would be $100. Because that gives me my restriction of 8 hours. And then if I plugged in 4, 0, that would be 30 times 4 plus 50 times 0, which gives me $120. So how many rakings and mulchings would maximize the income? Well, my maximum income is going to be at 4 mulchings and 0 rakings. That's exciting stuff, right? So let me show you what I got here for you. So your homework is this side of the worksheet that has 3 questions. Number 1 and number 2 are just like our first 2 examples, no story problem. Number 3 is a story problem. They even tell you what letters to use. Try to set up your equations. And then on the back side, there are 3 problems at the bottom here. You do not have to do those 3 problems, but I put this on here just so you would have another example of how to do linear programming. And so this is just like an extra example for you, but you need to do the 3 problems on the front. Okay? Tomorrow we're doing the last new thing of this unit, but it's also a new thing. It's 3 equations and 3 variables. So please try to be here because it's going to be like probably the most, I think, the hardest thing that we've done so far. So that's just my opinion. Hold on, let me stop recording.